In this lesson, we will learn about multivariate statistical techniques, discussing their theoretical foundations, assumptions, and practical implementations. We will see examples and datasets that illustrate how multivariate statistics can shed light on complex phenomena. Unlike univariate or bivariate statistics that focus on the analysis of a single variable, or the relationships between two variables, respectively, multivariate statistics encompass the analysis of at least three variables. This analysis is done by computer software for the most part, as the math involved is arduous. However, as we have done in previous modules, we can calculate some of the equations involved. This gives us a real sense of what the computer software is doing. At its core, multiple regression extends the principles of simple linear regression by considering multiple predictors instead of just one. Multiple regression is a helpful method for better understanding correlations between variables because the majority of outcomes of interest to nurse researchers are determined from numerous variables. The multiple regression equation allows us to estimate the value of the dependent variable, y, by incorporating the influence of multiple independent variables, each weighted by its corresponding regression coefficient. By plugging in the values of x1, x2, etc. into the equation, we can calculate the predicted value of y based on the intercept, a, and the estimated coefficients, b1, b2, etc. The least squares criterion is a principle used in multiple regression to determine the best fitting line or plane through the data points. It aims to minimize the sum of the squared differences between the observed values of the dependent variable and the predicted values based on the regression equation. In multiple regression, the goal is to find the values of the regression coefficients, b1, b2, etc. that minimize the sum of squared residuals, also known as the sum of squared errors. The residual is the difference between the observed value of the dependent variable and the predicted value based on the regression equation. The multiple correlation coefficient, R in multiple regression, is a measure of the strength and direction of the overall linear relationship between the dependent variable and the set of independent variables. It provides a summary of how well the independent variables collectively predict the dependent variable. The coefficient of determination, often denoted as R squared, is a metric used in multiple regression to assess the proportion of variance in the dependent variable that is explained by the independent variables. It quantifies the goodness of fit of the regression model and provides an indication of how well the model predicts the observed data. In multiple regression, R captures the overall linear relationship between the dependent variable and a set of independent variables. It accounts for the joint contributions of all the independent variables in explaining the variation in the dependent variable. Redundant predictors tend to inflate the value of R. This is because each predictor can individually contribute to the explanation of the dependent variable, but their combined effect may not add to the predictive power. As a result, R may appear larger than it actually is, potentially overestimating the strength of the relationship between the variables. Multiple regression relies on several assumptions that we have seen in other tests to ensure the validity and reliability of the results. The residuals should follow a normal distribution, and normality can be assessed using graphical methods we have used before in this course. The relationship between the dependent variable and the independent variables is assumed to be linear. This means that the change in the dependent variable is proportional to the change in the independent variables. The variance of the errors, the residuals, should be constant across all levels of the independent variables. In other words, the spread of the residuals should be the same for all predicted values of the dependent variable for multiple regression to yield the correct results. Computers are essential for multiple regression analysis due to their ability to handle large datasets, perform complex calculations and model estimation, and ensure reproducibility. StatCrunch can perform multiple regression, and although we will not compute these complex tests and our assignments for this course, we can see how a multiple regression is done with an example regarding predicting success in graduate school. Here we see a data set of 5 different variables. Unlike our simple linear regression example of using a midterm score to predict a final exam score, here we have 4 predictors of our outcome: the dependent variable, the GPA in graduate school. Once we have the data set loaded into StatCrunch, we can perform the multiple regression. Now, instead of selecting simple linear item from the regression menu of the Stat tab, we select multiple linear regression from the regression menu. This calls up the multiple linear regression dialog box where we can select our dependent variable, the grad GPA in this case, and then select all the independent or X variable predictors. We click Compute and StatCrunch will perform the regression. From the StatCrunch output, we can see all the results, including the regression equation, the p-value of the overall regression, the R-squared value, the F statistic it calculated. Using the regression equation it calculated, you can see the A value or intercept and all the weighted contributions by variable. So, we can take the individual values of X for each variable, such as an undergraduate GPA score of 3.5, and plug its contribution into the calculation of the outcome, the Y outcome, or the grad GPA value in this case, by just multiplying the 3.5 times 0.6716. We then repeat that for each predictor based on the B in the equation or the weights of each contributor, and we can predict the grad GPA. For each part of the regression model, the software summarizes the contribution of each predictor and its significance. Here, it appears that one's score on the math portion of the graduate record exam is not a significant predictor of one's GPA in graduate school. How did the software calculate the F statistic here, the value of 28.427? Well, there are several formulas for computing the multiple regression F statistic. The most convenient is shown on this slide. If we plug in the numbers, here we have 4 predictor variables, and we have 20 subjects in the dataset, so that's an N of 20. Using our calculator, we get an answer of 28.43 with this equation. If we look at our charts and tables guide, we see a multitude of other multivariate tests we can use in statistics. Here they are summarized by their name, purpose, measurement level, and the number of variables. These tests are also outlined in the remaining slides for this module. As we noted in the beginning of this course, our focus is on bivariate data. These multivariate tests are well beyond this introductory course, but one should be aware of their basic use and application. One note of caution here. Be careful to not confuse a variable for a group, or category of a single variable as we had in the ANOVA test of groups within a single interval ratio variable. Multivariate tests are for multiple, separate variables. Overall, multiple regression and multivariate analysis provide powerful tools for understanding the relationships between variables and making predictions. They offer valuable insights for researchers and health practitioners in various fields, helping them make informed decisions and draw meaningful conclusions from their data. In the next and last module, we will undertake the task of pulling together all we have learned in this course by analyzing a large data set with biomedical data.